Next, we can prove one of our big goals in the beginning material of this course, which is that holomorphic functions are analytic. We already showed that analytic functions are holomorphic, so then these two concepts are the same thing. Recall that analytic means that a function locally has a power series representation, whereas holomorphic just means the function has a complex derivative and that the complex derivative function is continuous. So to prove this, we're going to use the Cauchy Integral Formula, and we need to pull an infinite sum outside of an integral. So here's just a quick lemma from real analysis, I suppose, to address that issue. So if we have a sequence of continuous functions on a circle, so there's a circle radius r centered at z0, and each one of them has a bound, let's say mn, and if the sum of these bounds is finite, so this is mimicking the Weierstrass M-test, then we can pull the sum outside of the integral. And we're going to basically do this with power series to prove that holomorphic functions have power series representations using the Cauchy integral formula. So let's just quickly prove this lemma. It's very much based on the Weierstrass M-test, which is typically taught in real analysis. So by the Weierstrass M-test, this infinite sum of continuous functions converges uniformly to a continuous function, so that means the infinite sum makes sense and is a continuous function, so that's no issue. And now we can compare the integral of the infinite sum to partial sums, or an integral of a partial sum, but we know we can pull a finite sum outside of an integral, so that's no issue, or I can bring the sum back in. And then when I subtract the two, I get a tail of a sum inside the integral. I can go through with absolute values and get the integral of the tail of the absolute values. And since I've assumed that I can bound each one of these by mn, then I can bound the whole thing by the tail of a finite sum of positive numbers, and this tends to 0 as n goes to infinity. Okay, so we're just going to use this basic fact to prove a theorem which will give us something a little bit better than the theorem I already presented. So if I have a holomorphic function on a disk, then f equals a power series centered at z0 with radius of convergence at least r. So this says if f is holomorphic on a disk, then it equals a power series on that entire disk. So it's not necessary to shrink the disk or anything like that. So how does this go? We're going to basically try to look at the integrand in the Cauchy integral formula. So I'll fix a z with z minus z0 less than some r prime less than r. I just need a little bit of wiggle room, and because I don't know what's happening exactly on the boundary of the disk of radius capital R, I move in a little bit. So for a point on the circle of radius r prime centered at z0, I'm going to write the kernel that we use in the Cauchy integral formula as a power series centered at z0. So you just do some rearranging to get things in terms of z minus z0, and we've done something similar when we proved that 1 over z is analytic. It's basically the same idea. I factor out a w minus z0, and now this is starting to look like a geometric series, and so I write it like a geometric series, and I can do that because I have z minus z0 less than w minus z naught because this was r prime, and I'm assuming that z minus z naught is less than r prime. Okay, and so the terms here have this modulus, which this will play the role of mn in the previous lemma. Okay, so by the Cauchy integral formula, I can write f of z as this integral on the disk of radius r prime centered at z naught. And then I use my formula for 1 over w minus z, and I have the right bounds to apply the lemma. So I put in this infinite sum in for 1 over w minus z and pull the sum out. And what we have here is z minus z naught to the n, and these coefficients here. So notice this does not depend on z. These will give us power series coefficients for f. And so this was for any z in the disk of radius r centered at z naught, although I had to have a little bit of room to maneuver to start out with. The resulting thing is this integral, which I could, by previous results, this, you can change the radius you use here, and you could shrink it down. You could even take a limit as r goes to 0 if you want. But this gives the result because this is a power series. These are our coefficients, and these are the monomials in the power series. So kind of another way of stating, or I guess just a simple corollary of this, is that if I have a power series with radius of convergence finite, then f cannot be extended to a holomorphic function on a larger disk. Why is that? Because if I could extend it to a holomorphic function on a larger disk, I could represent it as a power series on that larger disk by the previous theorem, and that would contradict the radius of convergence. Also, we get from this proof the coefficient formula. So right here, I gave a formula for the coefficients. So if f is holomorphic on a disk, then it can be written as a power series there, and I can compute the coefficients using this formula for any r less than capital R. Finally, one more nice corollary we get from this are the Cauchy estimates, and these estimates seem crude at first, but they can do some interesting things. So the Cauchy estimates are here. If I have a function written as a power series with radius of convergence r, then for little r less than big R, I can get an estimate on the coefficients in terms of properties of the function. So I can bound it by the supremum of f on the disk, on the circle of radius r, divided by r to the n. That just comes from the coefficient formulas, because I do an is less than or equal to, let's see, I have a 1 over 2 pi I in front, so I'll turn that into 1 over 2 pi I. I can bound this like so. And what do we have here? So I can bound f by its supremum on this circle. And up here, I guess I should say the circle centered at z naught. So I can get sup over this circle centered at z naught of f. And this part in the bottom is equal to little r. But I also am integrating over the circle of radius r dw. So you get a 2 pi r, and you get a 2 pi r to the n plus 1. And so you exactly get the estimate up above, called the Cauchy estimates. Okay, and one bonus you can get out of this is you can actually put in an infimum, because you might as well choose an r that gives you the smallest value here. So in this slide, we've proven that holomorphic functions are analytic, and this is really powerful because now essentially anything you want to know about holomorphic functions that's local, you can do it with power series. On the next slide, we'll present some basic and important applications.